consumer behavior, utility, and the water-diamond paradox. Spoken version. Hello everyone, welcome back. Today we're going to look at part 2 of this course. In part 1, we looked at unsupervised learning and covered a lot of different types of it, including representation learning, clustering, and estimation for unsupervised learning. Now we're moving into a totally different paradigm of machine learning, perhaps a more popular paradigm, called supervised learning. From this lecture onwards, our focus is going to be primarily on supervised learning, where we'll learn a lot of algorithms and understand why certain algorithms work better than others in different situations. So what is supervised learning? As we've already touched on in the introductory video, let me recap it here. We have a bunch of data points, x1 through xn, where each data point lies in d-dimensional real space. This is our usual unsupervised learning dataset. You have features, sometimes called attributes, or what statisticians would call predictors or predictive variables. We'll just stick with the term features throughout this course. In addition to this, you also have supervision in the form of what we're going to call labels. These are values, y1 through yn, corresponding to each of the x1 through xn data points. So, you have some features, and you also have some labels associated with each one. This label information is the supervision part. And that's exactly why it's called supervised learning. In addition to just the data points themselves, we're also given some form of supervision alongside them. Now, what values can these labels actually take? There are different types of values labels can take, and depending on that, we get different types of supervised learning problems. If the labels take just two values, say from the set +1 or -1 or equivalently 0 or 1, since these are essentially interchangeable for our purposes, then such a problem is called a binary classification problem. It's called binary because there are only two possible labels. Given a new feature you likely haven't seen before, you'd want to predict whether its label is +1 or -1. In other words, you want to classify it as falling into one bucket or the other. That's why it's called a classification problem, and since there are only two labels, we call it binary classification. Of course, you don't necessarily have to have just two labels. But before we get into other types of classification, let's look at a simple example of binary classification. Given an email, classify whether it's spam or not spam. You somehow convert each email into a set of numbers. We'll discuss good ways to do this later. And treat these numbers as your features. Someone then reviews these emails and tells you which ones are spam and which aren't. The spam or not spam label becomes your y1 through yn values. Given a new unseen email, a spam classifier would then automatically determine whether it's spam or not. This is a classic binary classification problem. As I mentioned, you don't have to be limited to just two classes. You might have several possible classes instead. For example, you might have labels ranging from 0 through 9. When this happens, it's called a multi-class classification problem. Try to think of an example where labels might naturally fall into that range of 0 through 9. Pause and consider it before I give you the answer. One simple example is the digit classification problem. You might have a handwritten digit, and you want to classify which digit it represents. The image itself serves as your feature, and the label is the actual digit written in that image. People write the same digit in many different ways, and yet we still want a learning system to correctly recognize it. That's a multi-class classification problem. In general, we're not restricted to exactly the range 0 through 9. It could be 0 through some other number k. But the key point is that it's still a finite set of classes. The digit classification problem with labels 0 through 9 is just one standard example. Another popular type of supervised learning problem arises when the labels can be any real number, any value from -infinity to +infinity. When this happens, we call the problem a regression problem. This is perhaps one of the earliest types of supervised learning problems with deep roots in statistics. What might be an example of a regression problem? One where the features lead to a label that's a real number. Pause and think about it yourself first. Here's one standard example. Suppose your features include things like temperature, precipitation, and atmospheric pressure, and you want to predict the amount of rainfall on a particular day. That rainfall amount is a real number. It could be, say, 100.23 centimeters or any other real value. We'll refer to this regression example as rainfall prediction. Each of these types of supervised learning problems will require different types of algorithms, and I'll try to justify why different algorithms are needed as we move through the course. We'll start with the classically earlier supervised learning problem, regression. In this course, we'll spend a couple of weeks on regression and then focus for a longer stretch on binary classification. After that, I'll briefly discuss how ideas from binary classification can be extended to build models for multi-class classification. Multiclass classification won't be a major focus of this course, but we'll touch on some techniques for adapting binary classification methods to handle it. That said, the first thing we're going to start with today is the problem of supervised learning, specifically the problem of regression. Regression. So the input to a regression problem, often called the training data, is simply a set of points x1 through xn, where each xi lies in d dimensions, along with corresponding values y1 through yn, where each yi is a real number. That's our input. Now, what's the goal here? The goal of a regression problem is to learn how to make predictions for a new, unseen feature. In other words, we want to learn a function h that maps from d-dimensional space to the real numbers. Think of d-dimensional space as our feature space, since all our input features are represented as d-dimensional vectors, and the real numbers as our label space. We want a function that takes a given feature and produces a good corresponding label. So naturally, given our data, we want to learn a function that can be used to make predictions on future inputs. But here's the challenge: there are countless functions that map from d-dimensional space to the reals. How do we find a good one? That really comes down to a more fundamental question: how do we measure the goodness of a function in the first place? Suppose I hand you some function mapping from d-dimensional space to the reals and ask you how good it is for a particular dataset. At the end of the day, goodness has to be tied to the data somehow. You have the data in hand, but not the function. Yet if I give you a function, can you tell me how well it performs against that data? If we can answer that, then we can search for the function that performs best overall, the one that's essentially optimal for this dataset. This means we need some notion of error for a given function. Given some function h, we want a way to output a single number that tells us how good h is for this dataset. So what's a reasonable way to measure that error? Let's start with just one data point, the ith point in our dataset xi with corresponding label yi. Our function makes a prediction h of xi, and now we have two numbers h of xi and yi that we need to compare. One natural way to compare them is to look at the difference between h of xi and yi and square it. This gives us the squared error between our prediction and the actual value. This isn't the only reasonable way to define error. You might imagine other options, but we'll start with squared error and justify other choices later on. For now, it's worth noting we want this error to be non-negative. If we simply use the raw difference h of xi minus yi without squaring it, we could trivially make a function that always outputs negative infinity, driving the error arbitrarily low without actually learning anything meaningful. Such a function would be completely useless for prediction. So we choose our error measure more carefully. In this case, squared error. And we'll explore this in much greater depth later. That covers a single data point, but we actually have n data points. So a reasonable approach is to sum the squared error across all data points from I equals 1 to n. This gives us a reasonable starting point for measuring the overall error of a given function h with respect to our dataset. So now what's our goal? We want to find a function h that minimizes this error as much as possible. Here's a question worth pausing on: how small can this error actually get in the best case? Take a moment to think it through. The answer is that the error can go all the way down to 0, since it's a sum of squared, and therefore non-negative terms. Adding up non-negative numbers, the smallest possible total is 0. So when does this error actually reach 0? Which function h achieves that? If you think carefully about this error function, you'll realize that the h achieving 0 error is exactly the one where h of xi equals yi for every single data point. Only then do our predictions perfectly match the actual values, giving us 0 error. Now, here's the issue: we've defined an error function we want to minimize, and it turns out we can always construct a function h that simply outputs yi whenever given xi as input. That means our error on the training set becomes exactly 0. We've achieved perfect performance on our training data. So, if minimizing training error is really our whole objective, we're already done. But the real question is this actually a good function h? Are we truly satisfied with it with respect to the regression problem we actually care about? There are some real reasons to be skeptical here, and I'd encourage you to think about what might be problematic before I explain it myself. What's happened is that this function h has essentially memorized the exact mapping from each xi to its corresponding yi. For every training input, h simply recalls the exact correct outputs. But is memorization really what we're after? We might perform extremely well on our training data, our practice problems, so to speak. But when it comes to genuinely new test data, have we actually learned anything meaningful, or have we simply memorized the answers? In other words, we're essentially asking whether we are overfitting to the training data in a way that might hurt our performance on data we haven't seen before. At this point, it's not yet fully clear what overfitting precisely means, but it's becoming apparent that doing extremely well on training data doesn't necessarily translate into good performance on test data. Let's follow this line of thinking further. We've noticed that through memorization we can drive training error all the way to zero. But our actual goal was never simply to perform well on training data. Take, for example, a rainfall predictor that might perfectly predict rainfall for the past 3 years, yet be completely useless if it fails to predict rainfall accurately starting tomorrow. The entire point is to perform well on future, unseen data. Yet through memorization, we can trivially do well only on the training data itself. What we actually care about is performance on test data. So what exactly are we missing here? There are a few places where our reasoning might have gone astray. One choice we made was using squared error as our error function. Perhaps that's the culprit. Or if that's not actually the problem, where else might things have gone wrong, leading us toward memorization? If you think it through, the real issue isn't the squared error itself. The real problem is that we're allowing our search to range over absolutely every possible function mapping from d-dimensional space to the rails. If h is allowed to be any arbitrary mapping whatsoever, we will naturally end up finding a function that simply memorizes the data and consequently overfits. So how do we fix this? We can restrict the space of functions we're searching over. What does that actually mean in practice? It means we search only among certain structured functions mapping from d-dimensional space to the rails, essentially assuming that the true underlying relationship between inputs and outputs has a particular structural form. By imposing this kind of assumption, we deliberately narrow our search space rather than allowing every conceivable function as a candidate. So to be clear, our plan now is to keep using squared error, but additionally impose some structural constraint to shrink our search space. What's the simplest structural assumption we could reasonably make for a function mapping from d-dimensional space to the rails? One very natural and simple choice is a linear structure. In other words, instead of searching across the entire space of all possible functions from d-dimensional space to the rails, we now restrict ourselves to a much smaller subset. Let's call it h-linear. The set of functions from d-dimensional space to the rails that are parameterized by some vector w and are linear functions of the input. The simplest such linear function takes the form h sub w of x equals w transpose times x for any w in d-dimensional space. In one dimension, this is essentially just saying y equals m times x. You might reasonably ask, what about y equals mx plus e, which is also a linear relationship, just with an added offset? We can absolutely incorporate that too, writing it as w transpose x plus b. But for simplicity, I'll stick with the basic form w transpose x, understanding that everything we discuss can be easily extended to include that additional offset term later. So what does it actually mean to impose this kind of structure? Essentially, we're assuming that the true relationship between the input features and the output labels is fundamentally linear, even though there may be some noise in the observed output that makes the data deviate slightly from a perfectly straight line. Because we're hypothesizing this linear structure, we deliberately avoid searching across the space of all possible functions. Doing so would just end up fitting that noise too, which is precisely what overfitting looks like. Instead, we restrict ourselves purely to the space of linear functions. Given this, our new, refined goal becomes the following: we minimize over every h sub w in this restricted linear function space the very same squared error function as before. The sum of the squared differences between h sub w of xi and yi. Since h sub w is entirely parameterized by w, this is equivalent to searching directly over vectors w in d-dimensional space, minimizing the sum, from I equals 1 to n, of the squared difference between w transpose times xi and yi. This is still fundamentally a regression problem, but because we've restricted ourselves specifically to linear functions, it's now called linear regression. In essence, this has given a set of features. The best way to explain the corresponding label is through some weighted combination of those features, where the weights indicate how important each feature is. And combining them via w transpose xi should give a good approximation of the actual labels. Now, naturally, we can ask the same question as before: how small can this new objective actually become? As it turns out, this can still reach zero. It remains a sum of non-negative squared terms after all. But here's the key distinction: would reaching zero error in this restricted setting count as overfitting? The answer is no. Why not? Because this error becomes zero precisely when w transpose xi equals yi for every single data point, meaning our labels line up exactly with the structural relationship we've assumed, the linear relationship between inputs and outputs, with absolutely no leftover noise. In that case, we've genuinely captured the true underlying structure perfectly, which isn't overfitting at all. It's simply an excellent fit within the structure we've imposed. Overfitting, by contrast, would occur if we searched across a much larger space of functions than the true underlying relationship actually requires. That's when we'd start fitting the noise itself, rather than the genuine signal. We'll explore this notion of noise more rigorously from a probabilistic perspective later on. For now, it's enough to think of now simply as extra variation beyond what the true underlying structure accounts for. Variation that, from a prediction standpoint, carries no real meaningful signal.
So, how do we actually solve this problem? That's the next question. We set up the problem. Now let's figure out how to solve it. It'll help to think about the same objective in terms of matrices, since that makes things easier to work with. Let's define a matrix X where our data points are stacked as columns. That means X transpose is a matrix where the data points are stacked as rows. X1, X2, and so on up to Xn, giving us n different data points. So X transpose is an n by d matrix. We also have a label vector, y, which holds the corresponding label for each data point, an n by 1 vector. And our parameter, w, is a d by 1 vector w1, w2, and so on. Given the setup, we can rewrite our original objective as follows. We're trying to minimize the squared norm of the vector x transpose w minus y. Why does this work? Because x transpose w gives us x1 transpose w, x2 transpose w, and so on. Essentially a vector containing the dot product of w with every data point. We then compare this vector against y entry by entry, and squaring these differences is exactly the same as taking the squared L2 norm of the resulting vector, which lives in n-dimensional space. So our goal becomes minimize over w in d-dimensional space the squared norm, which we can also write as the vector x transpose w minus y transposed multiplied by x transpose w minus y. This is what's called an unconstrained quadratic optimization problem. It's unconstrained because we allow w to be any vector in d-dimensional space with no restrictions placed on it. It's quadratic because of the squared error term we chose. And it's an optimization problem because we're searching for the particular w that minimizes the subjective function. So how do we find that minimizing w? Since this is unconstrained and quadratic, the simplest approach is to take the derivative with respect to w. In high dimensions, that's the gradient. Set it equal to 0 and solve. In some cases, this gives a clean closed-form solution, in others, it might not. Let's see what happens here. Treating our objective as a function of w, we take its gradient. The vector of partial derivatives with respect to each component of w, where you fix one component, treat the rest as constants, differentiate, and then collect all these partial derivatives into a single vector. Working this out. And I'd encourage you to try this yourself. Gives us a gradient of 2 times x transpose w minus 2 times x times y. Setting this gradient equal to 0 gives us the equation x transpose w equals xy. So our optimal solution, w star, satisfies this equation. This means w star can be written explicitly, since it's essentially a matrix multiplied by w star equals x times y. Whether we can write this in fully closed form depends on whether that matrix x transpose is invertible. If it is, we simply pre-multiply both sides by its inverse. If it isn't, we instead use what's called the pseudo-inverse. For now, you can think of it much like a regular inverse. We'll dig into the pseudo-inverse itself a bit later. The pseudo-inverse essentially behaves like an inverse even when a true inverse doesn't exist, which typically happens when the matrix has a non-trivial null space but isn't full rank. In such cases, the mapping is many to one rather than one to one, meaning multiple inputs map to the same output. A true inverse would give you back a unique input for a given output in the one-to-one case, but when multiple candidates could map to the same point, the pseudo-inverse specifically picks out the one with the smallest possible length, which is why it's sometimes called the least norm solution. So, this gives us a genuine closed-form solution, and there's a lot to unpack about it as we move forward. The first thing worth noticing is a curious observation. What exactly does this w star depend on? It depends on the matrix x transpose. Now x is a d by n matrix, and x transpose is n by d, so x transpose ends up being a d by d matrix, essentially resembling a scaled covariance matrix. This is an interesting parallel to draw. Just like in PCA, w star depends on something covariance-like. But remember, PCA was entirely unsupervised, and that's an important distinction here. The key difference is that in this problem, we also have labels. And naturally, those labels should influence what w star looks like, since our whole goal is to match those labels as closely as possible. The labels enter the picture through y. So, similar to PCA, this covariance-like matrix for its inverse plays a central role. We'll unpack exactly what that role is later. But it's worth noting up front that the labels are also baked directly into this solution through y. Given a dataset, we can compute w star quite easily, even in code, since it's a closed-form expression. It might turn out to be computationally expensive in practice, which we'll get to shortly. But for now, we at least have this explicit expression for w star. So W star turns out to be a function of both the data and the labels, expressed as the pseudo-inverse of x transpose multiplied by x multiplied by y. It looks like a clean closed form, but we still need to properly make sense of what it actually means. Sure, we can observe that a covariance-like matrix is involved, but that's clearly not the full picture. We need a deeper, more meaningful understanding of this result. So how do we make better sense of it? We're essentially saying that linear regression has a closed form solution, which is genuinely useful. But now that we have the solution in hand, we want to dig deeper and understand exactly what it means. The first thing worth understanding is the expression itself, involving x transpose the pseudo-inverse times x times y, looks fairly complicated and deserves some kind of interpretation. So the first question is, can we describe this solution geometrically? The second question concerns computational considerations. A closed form solution is great, but recall that with PCA, we ran into certain computational constraints. Are there similar considerations here that we need to think through? The third question involves our underlying assumption that features and labels are related linearly. What if that's not actually true? What if instead we know the true relationship is quadratic or cubic? How should we think about modeling nonlinear relationships between features and labels? These are similar kinds of questions to what we asked with PCA, though naturally, given that this is a fundamentally different problem, the answers will have a different flavor. And finally, we touched briefly earlier on the idea of overfitting and on imposing structure to avoid it. But I was intentionally vague about what exactly we mean by noise. To properly understand noise, the right language to reach for is probability. So the fourth question is there a probabilistic way of understanding this entire problem? These are the 4 questions we'll tackle around linear regression. Once we've worked through them, we'll have a genuinely solid understanding of linear regression. One that will also let us build a more sophisticated version of it, leading to a couple of additional algorithmic refinements beyond the standard approach we've developed so far. Over the next few videos, we'll take on each of these questions in turn and work out the answers together. The first question about linear regression we want to ask is, what does this solution actually mean geometrically? Recall that the linear regression solution, W star, is given by the pseudo-inverse of x transpose times x times y. But what does this quantity actually represent geometrically? To understand this, let's work through a simplified example purely to make things easier to visualize. We restrict the dimensionality for this purpose, but everything we discuss here generalizes naturally to higher dimensions. Let's say we have just 2 features and 3 data points. In other words, 3 people, and for each of them, we're measuring 2 things, height and weight. Now picture a 3-dimensional space. In this space, let's draw one vector pointing in some particular direction. Call it F1, a 3-dimensional vector. Let's draw a second vector pointing in another direction. Call it F2, also 3-dimensional. Here's the key thing to notice: if I were to plot the actual data points themselves, each one would be a 2-dimensional point, since each person has just 2 features, height and weight. But that's not what I'm plotting here. Instead, I'm plotting 2 specific 3-dimensional vectors. What are these vectors? Well, our dataset consists of 3 people, each with a height and a weight. Let's call height feature 1 and weight feature 2. That means the heights of all 3 people taken together form a 3-dimensional vector, F1. Similarly, the weights of all 3 people together form another 3-dimensional vector, F2. In general, with n data points, these would be n-dimensional vectors. We also have a label vector, y, containing 1 label per person, y1, y2, y3, which is likewise a 3-dimensional vector. So we can put y here too, somewhere in the same 3-dimensional space. Now, in terms of regression, here's how to think about this. Suppose I pick a point that happens to equal 3 times f1 plus 2.5 times f2. That gives me some particular vector formed by combining height and weight in a specific way. I could pick a different combination, say minus 5 times f1 plus 3 times f2, and get a different point entirely. The exact numbers here are arbitrary. The point is that by varying these combinations, I can generate a whole range of different vectors. As I vary these linear combinations, I trace out an entire subspace, a 2-dimensional plane sitting inside this 3-dimensional space, specifically the plane spanned by f1 and f2. Every combination of the forms on constant times f1 plus on constant b times f2 lands me somewhere on this plane. Now there's one particularly special point on this plane. Like any other point on the plane, it can be written as a linear combination of f1 and f2, but it's special because it's the point that minimizes the distance to our label vector, y. In other words, I take my label vector y and project it onto the subspace spanned by the feature vectors. I'm essentially searching across all possible combinations of height and weight for the specific combination that lands closest to y. Note that y itself doesn't necessarily lie on this plane. It could sit anywhere in the surrounding space. So what we're really doing is finding the point within the plane that best explains y. So how do we characterize this closest point? First, since it lies on the plane, it must be expressible as some linear combination of f1 and f2. Say alpha star 1 times f1 plus alpha star 2 times f2 for some real numbers alpha star 1 and alpha star 2. We can write this more compactly using matrix notation if we stack f1 and f2 as columns and multiply by the vector containing alpha star 1 and alpha star 2, we get exactly this combination. Since this matrix of features is essentially X transpose, the special point can be written as X transpose times some vector alpha star. Now, since this is the closest point in the plane to y, there's a defining geometric property: the line connecting this closest point to y must be perpendicular to the plane, meaning it forms a 90-degree angle with every vector in that plane. Concretely, the vector y minus X transpose alpha star, the piece you'd need to add to X transpose alpha star to reach y, must be orthogonal to the plane itself. This means the dot product of this leftover vector with X transpose alpha star must be exactly 0. Expanding this out algebraically gives us a specific equation that alpha star must satisfy y transpose times X transpose alpha star minus alpha star transpose times X transpose alpha star must equal 0. Now here's the interesting connection: recall that our actual solution, W star, equals the pseudo-inverse of X transpose times X times Y. This is what we derived earlier by solving the linear regression problem directly. The natural question is, does substituting W star in place of alpha star actually satisfy this orthogonality equation we just derived? Working through the substitution is a bit tedious algebraically, but if you carefully expand everything out, making use of the fact that X transpose is symmetric, you can show that this expression does indeed equal 0. I'd encourage you to work through this derivation yourself as an exercise. So what does this tell us? It tells us that the point on our feature span plane that's closest to y is precisely X transpose times W star. That's the key geometric conclusion we're drawing here. So, geometrically speaking, X transpose W star is exactly the projection of the labels onto the subspace spanned by the features. That's the complete geometric interpretation of linear regression. Essentially, all we're doing is projecting our label vector onto the subspace spanned by our feature vectors. Of course, if y already happens to lie exactly within this plane, then its projection onto the plane is simply itself. The closest point in the plane, in that case, is y itself. It's worth thinking through, as an exercise, what it would actually mean for y to lie exactly on this plane, both in terms of the error function we defined earlier and geometrically. I'll leave that for you to work out. But this is the core geometric intuition behind linear regression. We set out with several questions to explore, and this first one concerning the geometry of the solution is now answered. We'll tackle the remaining questions in the videos that follow. Thank you.
Hello everyone. We've been looking at supervised learning, specifically the problem of regression. We posed it as a problem of linear regression, where we wanted to search for linear functions that best fit the data in the sense of squared error. We looked at the fact that linear regression can be solved in analytical form. That is, there's a closed-form solution, meaning W star can be written exactly as a function of x and y. Then we asked some questions about the nature of that solution and what more we can understand about linear regression. Toward that, we already looked at the geometric view of what it means to say that W star has a particular form, specifically x times X transpose, pseudo-inverse times x times y. We looked at the geometric interpretation of that. So now, in this video, we want to look at a few more questions about linear regression and try to address them. The first question we'll consider today is about the computational considerations of linear regression. Computational considerations. One good thing about linear regression is that we have a closed-form solution for the optimal W, which is of the form x times X transpose, pseudo-inverse times x times y. It's a great thing that we can solve this with just an equation. Given the data, we can compute x times X transpose, pseudo-inverse times x times y, and get W star, which we later use to make predictions on test data. However, the issue that might come up is how computationally expensive it is to compute this W star. If you look at the form of W star, the main culprit seems to be that inverse or pseudo-inverse computation. In general, you can assume this involves a regular inverse too, that's fine. This inverse computation is expensive if D is large. Remember, we made a similar comment when doing PCA, where we wanted to compute the eigenvectors of a covariance matrix. We said the eigenvector computation is typically expensive, on the order of D cubed. The inverse computation is exactly as hard as doing the eigenvector computation, because if you know the eigenvectors, you can actually compute the inverse very easily just by inverting the eigenvalues and so on. So the question is, how much time does it take? This also takes something like ordered d cubed. There may be more specialized algorithms that do it slightly faster, but in general, this is also going to take d cubed time, where d is the number of features. Remember, x times x transpose is a d by d matrix. So now the question is, if we can't do this inverse, how can we solve this problem? We know this is the solution, but we can't compute it because d is large, maybe d is a billion. You can't easily invert a billion by billion matrix, it would take too much computational effort. So the question is there a different way to get the same W star without computing the inverse? This is a very practical question to ask because at the end of the day, it's not just the theory that one needs to understand. Of course the theory builds the foundation, but the challenges that might arise when you actually implement something in practice are also worth keeping in mind. Now, without computing the inverse, can we do something? Well, we know that W star is the solution of an unconstrained optimization problem. Remember, W star is just the minimizer of the sum of squared errors, the average of the squared errors of the prediction, W transpose times xi minus yi. Now, W star can be any vector in d dimensions, and it's the solution of an unconstrained optimization problem. We can use general-purpose tools to solve unconstrained optimization problems to solve for W star as well. One of the most popular general-purpose tools to find the minimizer of a function is the method of gradient descent. Here's a very quick primer on gradient descent in case you're not familiar with it. Gradient descent is an iterative way to find the minimizers of functions using just first-order information. First-order information means the first derivative, when high dimensions, the gradient, which is just a vector of partial derivatives. So what is the gradient descent algorithm? You start at some point, some guess for your solution. Let's call that guess W0, some arbitrary point in d dimensions. Then you compute the gradient of the objective function at the point W0 where you are. The gradient tells you the direction in which you'd have to move so that the function increases the most. The direction given the highest increase is what the gradient points to. Now, we want to minimize the function, so naturally gradient descent tells you to move in the direction opposite to the gradient. The gradient tells you which direction climbs the mountain, so the negative of the gradient tells you the direction to move so that, before you reach the bottom of the mountain, we're reducing your function value. So the update rule is w at step t plus 1 equals w at step t minus the gradient of the function evaluated at wt. But you don't take a full step in the negative gradient direction. The minus sign says you move in the negative gradient direction, but then you scale it. You move some scalar amount times the negative gradient, where the scalar tells you how big a step to take in the direction pointed to by the negative gradient. The scalar is the step size. The property of this algorithm is that if you choose the step size carefully, then repeating this process, since it's an iterative algorithm taking a small step in the gradient direction at each new point, following wherever the gradient points next, you'll eventually reach what's called a local minimum of the function. A local minimum is a point where the gradient becomes zero. That doesn't necessarily mean it's the global minimum. For example, imagine a wiggly function. It might have one local minimum here, another local minimum there, and a separate point that's the global minimum. If you start near the first local minimum, you'll move toward it and stop there, because the gradient becomes zero and the update rule doesn't proceed any further. However, if your function is nice, not wiggly like that, but smooth with a single ball shape, then your gradient descent algorithm will converge to the global minimum no matter where you start, because there's only one global minimum, but every local minimum is also a global minimum. It turns out that for the function we care about, the sum of squared errors, it is in fact a function without wiggles. It's a quadratic function, and quadratic functions belong to a class of functions called convex functions, which have a unique global minimum in this case. That means every local minimum is a global minimum, so your gradient descent algorithm will in fact converge to the optimal point. So this is an alternate way to solve the same problem. The question is, does it solve our original problem, the one about computing inverses? We're now saying we don't need a one-shot closed-form solution, an equation, instead we'll do it iteratively, but the inverse computation should go away. Is it actually going away in this case? Let's see. You may want to pause here and think about it before I explain the solution. So what is the function we care about? A function, f of w, is simply the squared norm of xw minus y, which equals the sum from I equals 1/10 of the quantity w transpose times xi minus yi squared. We already saw that these two expressions are the same. Now for this function, one can compute the gradient. The gradient works out to 2 times the quantity x times x transpose times w minus 2 times x times y. This is a straightforward exercise, please verify it yourself. You just take the derivative of the function with respect to each component of w and collect the partial derivatives into a vector, and that gives you exactly this result. If you're not that comfortable with partial derivatives, it's a good exercise to try. So what does this tell us? It tells us that the gradient descent update rule for linear regression looks like this: w at step t plus 1 equals wt minus some constant scalar, call it e to t, times the quantity 2 times x transpose times w, minus 2 times x times y. That factor of 2 isn't particularly important. You could have defined the original function with a factor of 1/2 in front, and the 2 would cancel out. That's common practice, but here I'm not doing that. It wouldn't really matter, since the 2 can just be absorbed into the constant. The steps work the same either way. The good thing here is that there's no inverse computation happening. As you can see, w at step t plus 1 is wt, the current value, minus some scalar times a quantity that doesn't require computing an inverse. So we're not computing the inverse at all. We'll converge to w star through this process, which effectively achieves what computing the inverse directly, x times x transpose inverse times x times y, would have given us. We're mimicking that result, not in one step, but across multiple steps through the gradient rule, and eventually we converge to the same w star. That's a good thing. Computationally, we're never computing the inverse. So even if d is much larger, even in the millions, you can still run this algorithm. That addresses the case where the inverse computation is the bottleneck. Now one might also ask, what if instead n is large? We solved the d being large problem by switching to gradient descent, but what if n is large? Remember, n is the number of data points, let's say hundreds of millions. Is there an issue here? Well, remember, gradient descent is an iterative process, so at every round you need to compute the gradient. Computing the gradient requires x times x transpose, and while x times x transpose is a d by d matrix, it comes from multiplying a d by a matrix with an n by d matrix. So there's an interdependency hidden inside computing x times x transpose itself. If n is in the billions, even computing x times x transpose might be difficult. So we may want to avoid computing x times x transpose altogether, not just its inverse, if we have a huge number of data points. So now the question is, it seems like we can't even run gradient descent because it needs x times x transpose, which may itself be computationally expensive. The question then becomes, how do we adapt gradient descent to the situation? Can we somehow mimic gradient descent while getting rid of the need to compute x times x transpose? The surprising answer is yes. You can get rid of both the d problem and the n problem, the d problem by using gradient descent, and the n problem by using a variant of gradient descent that's very popular in practice. Let's look at what this variant is. This variant is called stochastic gradient descent. It's a variant of gradient descent. There are several variants, and I'll give you one simple version here. Like gradient descent, it's an iterative algorithm. For t equals 1, and so on, up to some capital T, you can run this for a fixed number of rounds or use some convergence criterion, similar to standard gradient descent. Let's say we have a budget of rounds we want to run this algorithm for. Now, what stochastic gradient descent does differently is that at each step, you first sample a batch of, let's say, k data points uniformly at random from the full set of data points. What does this mean? Suppose you have a billion data points to start. Let's say k is 100. We're going to uniformly sample 100 data points from that billion. This can be done efficiently, since you're just picking 100 random indices out of a billion, which is fast. Once you have those 100 indices, you fetch those 100 data points, assuming your data is stored reasonably well. That's not a big issue. Now, here's the interesting part. Instead of working with a billion data points, you pretend that the small sample is the entire dataset, and you take a gradient step with respect to just this sample. So the gradient at step 2 now looks like this: 2 times, not x times x transpose, but x tilde times x tilde transpose times wt, minus x tilde times y tilde. Here, x tilde is just the small batch of data points sampled in this round. So instead of being an n by d matrix, it's just a 100 by d matrix, not a billion by d matrix, because you're only sampling 100 data points. So what we're doing is pretending that, for the step, you only have 100 data points to look at, and you take a gradient step as if you were trying to minimize the squared error with respect to only the smaller data set. You take a gradient step that works well for just the sample. This is manageable because x tilde is a d by k matrix, where k is small, the number of sample points. That's the algorithm. You run this for t rounds. Note that at every round, you sample k points, and these points are different each round. That's the important part. Every round you get a different uniformly random sample from the full set of points, and you move in the gradient direction with respect to whatever sample you got that round. Now, you could argue that the sample's gradient is a noisy version of the true gradient. Because you're doing uniform sampling, you get a noisy version of the original gradient and you're moving in a noisy direction. So the question is, does this noise cancel out over time so that overall you still make progress toward the true W star that standard gradient descent would reach? The surprising and reassuring answer is yes. There's one small caveat. In standard gradient descent, you start with some W0, move to W1, W2, and so on up to W at round T, and after T rounds, you output that final WT. But here, because at every round there's a chance you get a noisy gradient and might move in an unlucky direction, just taking the very last WT might not be a good idea since your last sample could have been unlucky and pushed you in a bad direction, away from the minimizer. So instead, after T rounds, you use as your final answer the average of all the W values you've seen so far, rather than just the last one you computed, as you would in standard gradient descent. Now, what can we guarantee about this output from stochastic gradient descent? We can guarantee that this average is guaranteed to converge to the optimum W star with high probability. Because randomness is involved in picking the data points, we have to deal with probability here, but the guarantee is that you converge to W star with very high likelihood. That's a good result. So, we've gotten around both the D problem and the N problem, first by switching to gradient descent, and then by switching to its stochastic version, and this works very well in practice. That batch size, K, is what's called the batch size, and depending on how much computation you can afford, you can increase or decrease it. The guarantee holds regardless of the batch size, though a smaller batch size generally means you'll need more rounds to reach the minimizer compared to standard gradient descent. Still, this extra computation is much more manageable than computing x times x transpose directly, which can be very expensive when n is large. This algorithm is called stochastic gradient descent, and that's what I wanted to cover regarding the computational considerations of an algorithm like linear regression. We'll now move on to a couple more questions about linear regression. The next topic we'd like to discuss is, why linear regression? Why did we choose a linear relationship, and why not something more general, not necessarily linear, between the features and the output variable y? What if, for instance, the relationship is quadratic, or something like that? That leads us into what's called kernel regression, similar to how we did kernel PCA. We're going to look at a kernelized version of linear regression, which is very similar in spirit, so we'll try to understand kernel regression next.
Let's try to understand nonlinear regression now. By nonlinear, I mean, let's say we have a hypothesis that the actual relationship between the features and the output isn't necessarily linear, it's not W transpose times X. Instead, there's some more complicated relation. Maybe height and weight are your features, and what actually explains your label Y is something like height squared plus 3 times weight minus weight squared, or something along those lines. In that case, linear regression will fail because it can't capture squared terms or a cross term like height times weight, even if that cross term is important for explaining Y. You can still run linear regression, but even the best W you find will make a lot of error, both on your training set and your validation set. So how can we do nonlinear regression? Remember, our idea for moving from linear PCA to nonlinear PCA was through the notion of kernels. We're going to do the same thing here. The trick there was to write the optimization problem for PCA, what do you want to get out of PCA in terms of dot products between data points. Once we could do that, we could use a kernel matrix to replace the dot product, which effectively meant we moved to a higher dimension and did PCA there. That was our kernel PCA algorithm. We're going to do something similar here. It's as if you want to map your data points to a higher dimension and then learn a linear regressor in that higher dimension, but without explicitly computing those high dimensional mappings. So how can we do that? We can do it if our regression solution can somehow be written in terms of dot products between data points. But what is the regression solution itself? It's x times x transpose, pseudo-inverse, times x times y. That's the vector we have, and as it stands, it doesn't depend directly on dot products. X times x transpose is a D by D matrix, whereas a dot product matrix would be an N by N matrix containing a pairwise value for every pair of data points. That's not what we have here. But we know, from our geometric considerations and by thinking about it a bit more, that W star, the solution to this linear regression problem, must lie in the span of the data points. Let me state that and then explain it. First point to note, W star must lie in the span of the data points. Why is that true? What does it mean to say W star lies in the span of the data points? Suppose you have a bunch of data points in D dimensions, so W star is also a vector in D dimensions. If all the data points happen to lie on a plane in 3-dimensional space, then W star would also lie on that same plane. Let's picture this. Suppose you have 3-dimensional data points, but they're not spread across the full 3-dimensional space, they actually lie within some 2-dimensional plane sitting inside that 3-dimensional space. So all our data points lie within this plane. Now the question is, will W star also lie on this plane, or could W star lie outside it? Suppose, for the sake of argument, that W star actually lies outside this plane. Remember, W star is the one that minimizes the sum of squared error. The sum over I of W star transpose times xi minus yi squared is the smallest possible among all possible choices of W. Now, if this W star is actually outside the plane, let's look at a new vector, call it W tilde, which is the projection of W star onto the plane, the closest point to W star that lies on the plane. Let's ask, how does W tilde transpose times xi minus yi compare to the same expression using W star? Well, the value using W tilde cannot be strictly smaller than the value using W star, since by definition W star already gives the smallest possible value because it solves this problem. So the right-hand side can't be less than the left. But what's the actual relationship between the two? If you think about it, since W tilde is the projection of W star onto the plane, we can write W star as W tilde plus a perpendicular component, let's call it W tilde perpendicular. Adding these two together gives back W star. This perpendicular component is orthogonal to the plane, meaning it's orthogonal to every point on that plane. So, W star transpose times xi equals W tilde transpose times xi plus W tilde perpendicular transpose times xi. But since the perpendicular part is orthogonal to every xi in the plane, that second term is 0 for every I. So for any data point, the dot product that W star makes with the data point is exactly the same as the dot product that W tilde makes with it. That means the predictions made by W star and W tilde are exactly the same for every data point, which means the error they each produce on the training data is exactly the same. So I might as well use W tilde instead of W star, it works just as well. So, without loss of generality, we can assume that our original W star actually lies on the plane, or more generally, in the span of the data points, since a version of W star that does lie in that span is just as good for our predictions. So we'll use that version going forward. What does this mean? It means W star equals some linear combination of the data points. Since the data points lie in a plane or subspace, our linear combination of them can give us W star. So W star equals x times alpha star for some alpha star in Rn, meaning a vector with n components since there are n data points and x is a d by n matrix. So you're taking all the vectors in the dataset, weighting them, using the values alpha star I for the ith data point, adding them up, and that gives you W star. But remember, we also know that W star equals x times x transpose, pseudo inverse times x times y. This comes from our gradient analysis. We took the gradient, set it to 0, and solved for W star. So this means x times alpha star equals x times x transpose inverse or pseudo inverse times x times y. Now we want to get rid of that x times x transpose term. We'll pre-multiply both sides by x times x transpose to get x times x transpose times x times alpha star equals x times x transpose times x transpose pseudo inverse times x times y. These last two terms cancel out, since that's the property of a pseudo inverse. Multiplying a matrix by pseudo inverse gives you the identity. So this simplifies to x times x transpose times x times alpha star equals x times y. That's where we are right now. The overall goal is to write everything in terms of x transpose times x. We have that term here, but there's also an extra x on the other side, so we'll pre-multiply the whole equation by x transpose. This gives us x transpose times x transpose times x times alpha star equals x transpose times x times y. Now we have something nice, since the term x transpose times x appears twice on the left and once on the right. So we can rewrite the whole left side as x transpose times x squared times alpha star equals x transpose times x times y. Now x transpose times x is our kernel matrix, let's call it k. So this equation becomes k squared times alpha star equals k times y. In other words, if k is invertible, then alpha star simply equals k inverse times y. So what's the use of all this? We solved for alpha star, which tells us how to combine our data points to get W star. We're saying that if you have a kernel matrix, the way to combine the data points is given by the inverse of the kernel matrix times y. Now what's this useful for? The whole point is that when you make a prediction for a new data point, say x test in d dimensions, the kernel approach says you need W star transpose times y of x test. That is, you'd map x test to a higher dimension and take a dot product with W star, the best W star that minimizes squared error across all the data points mapped into that higher dimensional space. So W star would be the minimizer, the argument over the sum from I equals 1 to n 5xi transpose W minus yi squared. This means you take a dataset, map every data point to a higher dimension, and solve a linear regression problem there to get W star. Then, for a new data point x test, you'd map it to that higher dimension and take the dot product with W star. However, we don't want to do that. We can't afford this explicit mapping, that's the whole theory of kernels as we've seen before. So can we make this prediction without explicitly using phi? That's exactly what our alphas help us do, thanks to the fact that W star equals the sum from I equals 1 to n of alpha star I times phi of xi. That's what it means to say W star is a linear combination of data points in a high dimensional space. So W star transpose times phi of x test, our prediction can be rewritten as the sum from I equals 1 to n of alpha star I times the kernel evaluated at xi and x test. So you have a kernel function which, given any two data points, evaluates the dot product in the high dimensional space, and alpha star is simply obtained by solving k inverse times y, where k itself is an n by n matrix, evaluating the kernel across the dataset, much like we did for kernel PCA. The extra thing here is that y also matters now, which makes sense, since this is supervised learning rather than unsupervised, so the labels come into play. So how would you actually do linear or nonlinear regression with this approach? The algorithm is quite simple. You're given a bunch of data points and a kernel function. You evaluate the kernel function across all pairs of data points to get the n by n matrix K. Then you compute alpha star as k inverse times y. Once you have alpha star for a new data point, x test, you simply compute the prediction as the sum from I equals 1 to n of alpha star I times the kernel function evaluated at xi and x test. You can think of the kernel function as measuring how similar two data points are. So this prediction is saying, given a new test point, we look at how similar it is to each of our training data points. That's what the kernel evaluated at xi and x test tells us. But then we also ask, how important is that training point to W star, which is captured by alpha star I? So alpha star I tells us how important the ith point is to W star, and the kernel value between xi and x test tells us how similar x test is to xi. A test point might be very similar to a data point that isn't very important for W star. So it's the product of these two things that matters for our prediction, and we sum that up over all the data points. By choosing different kernels, quadratic kernels, cubic kernels, Gaussian kernels, or whatever kernel you prefer, as we've seen earlier, you can solve the regression problem in any higher dimensional space you like. That's the power of kernels. So what we've managed to do is kernelize our linear regression problem to handle nonlinear regression as well. So that covers the relationships between features and how they explain the output variable. So far we've looked at three different aspects. First, the geometric consideration, understanding W star as the projection of the labels onto the subspace band by the features, giving us x times W star. Second, computational considerations, where we arrived at the stochastic gradient descent algorithm. And now, if you want to capture nonlinear relationships among features that explain the labels, you use kernel regression, going from PCA to kernel PCA, and now from regression to kernel regression. So those are some of the aspects we've covered. Now we'll look at one more aspect of linear regression, another powerful one, which will actually lead us into several more interesting variants of this linear regression problem. That's introducing something we haven't seen yet in linear regression, namely introducing probability into linear regression. Right now, everything has been deterministic. So what happens when we look at linear regression from a probabilistic point of view? That's what we'll see next.
Now what we're going to see is a probabilistic view of linear regression. What happens when we think of linear regression as if there's some probabilistic model generating our labels? That's what we're going to look at. We've already looked at estimation in general in an unsupervised setting where we've seen maximum likelihood, Bayesian methods, and so on. Now we're going to think of linear regression in the same way as an estimation problem. That means we're going to assume there's some probabilistic mechanism generating what we've observed. So what exactly are we going to assume? In the linear regression problem, you have data points in d dimensions and labels that are real numbers along with a dataset which I'll write as x1, y1, and so on up to xn, yn. That's our dataset. The probabilistic model we're going to assume is this: the label given the data point is generated as w transpose times x plus some noise epsilon. What does this mean? It means we're not trying to model how the features themselves are generated, we're only trying to model the relationship between the features and the labels in a probabilistic way. So what's the mechanism that generates the label if we're given x? We're going to hypothesize the following. If you give me a feature, there's an unknown but fixed w, not known to us. This is the parameter of the problem, unknown but fixed, living in RD. Whenever we see a feature, we compute w transpose times x, but y isn't exactly equal to that. That's the structural part of the problem. We're also explicitly saying there's a noise component. We add some noise to w transpose times x, and that's our epsilon. This noise is assumed to follow a Gaussian distribution with zero mean and some known variance, sigma squared. So the noise is Gaussian. So what we're saying is that every yi in our dataset was generated by this process. We were given xi, and to get yi, there's an unknown but fixed w such that w transpose times xi was computed, and then noise was added. We only observe the noisy version of w transpose times xi, while we know the statistics of the noise, zero mean, known variance sigma squared. The only thing unknown to us is w. So now we can view the whole thing as an estimation problem. What are we trying to estimate? We're trying to estimate w, which, after noise is added, determines our labels. Once we've specified a model for how the data is generated, meaning how y is generated given x, and we have an unknown parameter, we can bring in methods we already know for coming up with estimators. The simplest approach here, as you might guess, is the maximum likelihood approach. So let's look at the same problem through a maximum likelihood lens and see what comes out of it. The standard maximum likelihood setup requires writing down the likelihood function. The parameter of interest is w, but the likelihood function also depends on the data x1 through xn and y1 through yn, since those are the observed data points. We're treating the likelihood as a function of w, even though it technically also depends on the data points and labels, and we'll try to find the w that maximizes the likelihood of seeing this data. So what is this likelihood? As usual, we assume the data is independently and identically distributed, meaning x1, y1 is generated independently of x2, y2, and so on, all from the same underlying distribution. So the likelihood is a product from I equals 1 to n of the probability of observing a particular yi given xi. We know that each yi given xi is generated as w transpose times xi, a fixed quantity with nothing random about it, plus random noise. This noise has zero mean and a certain variance. If you add a fixed constant, w transpose times xi to a zero mean Gaussian, the mean shifts but the variance stays the same. For example, if you have a zero mean Gaussian and add 5 to it, you get a Gaussian with mean 5, same variance. It's exactly the same idea here. Since we've added w transpose times xi to a zero mean Gaussian for the ith data point, the result is a Gaussian distribution with mean w transpose times xi and variance sigma squared, which we assume is known. So the likelihood can be written using the Gaussian density proportional to e raised to the power of negative, the quantity w transpose times xi minus yi squared divided by 2 sigma squared, along with the usual normalizing constant, 1 over the square root of 2 pi sigma. That normalizing constant won't actually matter for our maximization, as we'll see. Once we've written down this likelihood, we can take the log likelihood, log L of w, with respect to the same parameters, x1 through xn and y1 through yn. We take the logarithm because it's easier to work with sums than products. This gives us a sum from I equals 1 to n, where the log cancels the exponential, leaving us with negative, the quantity w transpose times xi minus yi squared, divided by 2 sigma squared, plus the log of the normalizing constant, 1 over the square root of 2 pi sigma. Remember, we want to think of this as a function of w. The data, x, is constant, sigma is constant, and y is constant, so this expression is purely a function of w. We want to find the w that maximizes this log likelihood. So, equivalently, to find the best w, we want to maximize over w the sum from I equals 1 to n of negative, the quantity w transpose times xi minus yi squared. And dropping the constant scaling factor since sigma squared is assumed known and constants don't affect where the maximum occurs. This is equivalent to minimizing over w the sum from I equals 1 to n of the quantity w transpose times xi minus yi squared. This minimization problem is exactly the linear regression problem of squared error that we've already worked with, which means we already know its solution. So what is the solution here? The maximum likelihood estimator, w hat sub ml, turns out to be exactly the same as our w star, which we already know equals x times x transpose, pseudo-inverse times x times y, from our earlier discussion of linear regression. It's a nice result that we started from a completely different angle, thinking of a probabilistic mechanism generating y given x, and then applying the natural approach of maximum likelihood, and we arrived at exactly the same solution as standard linear regression. So what's the conclusion here? This is worth stating clearly because there are some interesting points to draw out. The conclusion is that the maximum likelihood estimator, assuming, and this is the important part, zero mean Gaussian noise, is exactly the same as linear regression, and again, this is the important part, the squared error. We could have either solved the linear regression problem using squared error directly, or treated it as a maximum likelihood problem assuming zero mean Gaussian noise, and both approaches are exactly equivalent. Understanding that equivalence is important because what makes them equivalent is specifically the choice of squared error. When we originally introduced linear regression, we didn't really justify using squared error beyond it being an intuitive choice. Now we're saying that beyond intuition, it has solid probabilistic backing. We're saying that choosing squared error to solve the linear regression problem is implicitly the same as assuming there's zero mean Gaussian noise added to our labels corrupting them. Both directions of this connection matter. If we had reason to believe the noise wasn't Gaussian, then solving the maximum likelihood problem would no longer be equivalent to using squared error in linear regression. The assumed noise distribution effectively determines the loss error function we should be using in our regression. That's the connection I want you to take away here. For example, if we had assumed a different noise distribution, say Laplacian noise instead of Gaussian, then the resulting maximum likelihood problem would no longer be equivalent to linear regression with squared error. It would correspond to a different loss function. If you use Laplacian noise, it turns out you'd instead be looking at the sum of the absolute differences between W transpose times Xi and Yi, rather than the squared differences. That would be the actual problem you'd end up solving. This is because the Laplacian density has an absolute value inside its exponential e to the power of negative the absolute value of W transpose times Xi minus Yi, and it falls off more sharply than the Gaussian distribution, though the detail isn't the main point. The main point is that choosing a noise distribution implicitly chooses an error function, and choosing an error function implicitly chooses a noise distribution. That's the first important connection to draw from this probabilistic view. The next question is this the only benefit we gain from viewing linear regression probabilistically, or do we gain something else too? The answer is yes. This is an important conclusion. Viewing W as an estimator lets us connect noise and loss. But what else have we gained? The most important additional benefit is that now we can study the properties of this estimator, specifically the properties of W hat sub ML. This is a significant gain from viewing learning as a probabilistic mechanism, because the moment you frame learning probabilistically, it becomes an estimation problem, and once you have an estimator, you can bring in everything we already know about analyzing estimators. We've already looked at what makes a good estimator and what might not. So now the question is, can we use this notion of estimators and properties of estimators, or perhaps other estimation approaches, to better understand the problem of linear regression? That's exactly what we'll look at next.
Hello everyone, welcome to the Week 5 Companion Notebook. This week we'll go through the linear regression least squares method and the kernel regression method. We'll start with the linear regression algorithm. For this algorithm, we'll use a dataset X as our data and Y as our labels. The mapping between X and Y is shown in this plot, and as you can see, this mapping follows a linear function. Before moving on to the algorithm itself, let's first discuss the loss function. The most commonly used loss function for regression is the sum of squared errors, given by this equation. To understand this loss function further, we'll take y equals x as a baseline model, where w is simply 1. Here's the plot for this baseline model, and as you can see, this is the w vector, and these are the residuals. Calculating the loss function using this formula, we get a loss of 10.6. Now let's look at the least squares closed form solution. It's attained by optimizing the error function itself, minimizing the error function with respect to w. This function can be written in terms of w as follows. Taking the gradient with respect to w, we get this equation. Setting the gradient to 0 gives us this equation, and solving it for w, we finally arrive at the solution w star equals x times x transpose, pseudo-inverse times x times y, where the pseudo-inverse refers to the pseudo-inverse of x times x transpose. Now let's use this least squares closed form solution on our dataset. Before that, we'll add a row of 1s to account for the bias in our dataset. Plugging in the values of x and y into the closed form solution and solving for w, we get this as the final step, and this is our final w, the one we obtain using least squares regression. Now let's find w using gradient descent instead. Remember, w star is the solution of an unconstrained optimization problem, and we can solve it using gradient descent given by this update equation, where t represents the iteration number and eta is the scalar that controls the step size. Eta is a hyperparameter that we choose through experimentation. In this case, we've selected eta to be 0.1. Plugging the values of x, y, and eta into this equation and solving for w, we get w equal to 0 and 2.02 in just one step. Note that we initialized w at step 0 as a vector of zeros. Here's the plot of the regression line using gradient descent. Since gradient descent and least squares regression gave us the same w, they produce the same plot. Now let's move on to the kernel regression algorithm. For this, we selected a different dataset, where x is given here and y is given here. Plotting x against y, we see this plot, and as you can see, the mapping is somewhat quadratic. So let's use kernel regression. We know that w can also be represented as a linear combination of all the data points with a coefficient vector given by alpha, where alpha belongs to Rn. Solving that equation further, we get alpha equals k inverse times y, where k is x transpose times x. This k can also be obtained using a kernel function like the polynomial kernel or the RBF kernel. Let's use the polynomial kernel of degree 2 on our dataset. Here's the polynomial kernel of degree 2, and solving further, we get k equal to this matrix. Now let's find alpha using the equation we found earlier, k inverse times y. Plugging in the values of k inverse and y, we get alpha equal to this vector. Now let's find the predictions using alpha. We know that we predict the values of y using w transpose times phi of x, but this expression is also equivalent to alpha times k, or k transpose times alpha. So we use the formula k transpose times alpha, plug in the values of both k and alpha, and finally get our predictions. As you can see, these are very close to our true labels. When we plot our regression line, you can see it follows a quadratic function, and our true data points sit very close to the regression line itself. Now let's try to solve a numerical problem. Suppose kernel regression with parameter sigma squared equal to 1/2 was applied to the following dataset with two features where x equals this matrix and y equals these labels. The weight vector can be written as w equals phi of x times alpha, where phi of x is the transformation mapping corresponding to the kernel. The vector alpha is given by this matrix obtained from k inverse times y, where k is the corresponding kernel matrix. What will be the prediction for the point 1 transposed? First, we'll simplify the kernel function itself. The kernel function is originally given by this expression, but since we know the value of sigma squared, we plug that in and simplify it to this. Now, this is how k transpose times alpha is written, and terms like k1 test, k2 test, and so on can be solved from here. After solving for k of x1 and x test, if we plug in the values, you can see the Euclidean distance is 1, so we get e raised to the power of -1 here, and likewise for the other terms. Solving this dot product, we get this as our output, and after further calculation, we arrive at the conclusion that k transpose times alpha equals 3. Now let's implement what we learned in the companion notebook in Jupyter Lab. We first load our dataset and assign it to the variables x and y. Plotting it, we get this plot, and as you can see, it follows the same linear mapping as before. We add the column of 1s first, and the new x matrix looks like this. Then we obtain w using the closed form solution for least squares regression, and w comes out the same as what we saw earlier in the walkthrough. Now we use gradient descent to find the optimal w. The eta value is declared here, w grad is initialized to a vector of zeros, and we run it for one iteration. Finally, we get w to be the same as the closed form solution. Plotting the optimal w, we get this picture, and as you can see, the predictions are very close to the true labels. Now we move to the kernel regression algorithm. The dataset is declared here, and after plotting it, you can see the dataset follows a quadratic mapping. We first compute the value of k using the equation from before, and we get k here. Next, we compute the value of alpha using k inverse times y, and this is the resulting alpha vector. Now the prediction is done using k transpose times alpha, giving us the following predictions, and as you can see, they're very close to our true labels. Plotting the kernel regression line, you can see it follows a quadratic function, and the true labels sit very close to the predictions themselves. Banco.